Hello, ladies and gentlemen. I'm Mr. G, and today we're going to learn about minerals. Okay, so for this, you should have this. It is called Rocks and Minerals. It probably has the number 90 up at the top. This is a note packet, guided notes that we'll be filling in as you go. Okay, so minerals. What are minerals? Okay, so the first thing I want to point out is typical confusion that students often have. It's minerals versus rocks. Okay, so it's oftentimes a kid will call a mineral a rock. Let's talk about some of the differences here. So for instance, what I would often do, and I don't have it with me today, is I would walk around my classroom with one of these in my hand. And then I say, isn't this a great wall? Look at this wall here. It is a typical red wall you often see. And that probably is happening to you right now. It's sort of not jarring with your brain. You're like, what are you talking about, a wall? It's a brick. And that's right. So that is a brick, and bricks make up walls. And that's the same way that minerals make up rocks. So in this case, the brick would be the mineral and the wall would be the rock. Another example, you look at this and like, man, look at that flock. Man, that's such a great flock. And people look at that and say, that's not a flock. This is a flock, right? So birds would be the minerals, and many birds together make up a flock. That would be the rock in this case. Or you say, oh man, look at that guy. Check that guy out right there. So cool, such a cool guy. That doesn't make any sense. That is a cell. But I go, look at that guy. That's a cool guy right there. Okay, so cells make up people the way that minerals make up rocks. That's a good sort of introduction. So sometimes it can be difficult to tell them apart, but basically minerals make up rocks. So here we go. Some minerals, in some extreme cases, can be like this. This is the subway garnet from excavation of the subway in the late 1800s. They found this huge garnet crystal. Look at that. It's close to almost a bowling ball size, super cool, and very famous. So these are these extreme examples of why minerals can be really cool. Here is another example, and this right here is a mineral that we as humans, you and I, eat. Sounds crazy, you're eating a mineral out of the ground, but we commonly eat it. Can you think of what mineral this is? Let me show another picture of it. This is an extreme close-up picture of how we may often see it in a typical kitchen. And this is the mineral halite, and you and I may know it as table salt. Pass the salt shaker, put it on your food. That's what that is. That's actually a mineral out of the ground, which is always really interesting. Probably the only real mineral that we tend to eat. All the other ones we should not eat. So, in the note packet here, let's talk about this just a bit. So, rocks are made of minerals, and minerals are made of atoms. Okay, so we're going to get smaller. That's what minerals are made of. Now, we can't really see atoms. They're microscopic or even smaller than microscopic, but atoms make up minerals, and minerals make up rocks. So here's the example here. Minerals are to rocks as bricks are to, you probably know it from before. We're going to fill it in right now. Walls. So make sure you're copying this as you go. Most minerals in rocks are very small. They are usually so small you can't see them with your naked eye. You would need some sort of magnifying lens or sort of microscope to look at them. So, but some rocks have minerals that are quite large. Now, I'm not sure how well you'll be able to see this in the camera, but this rock here is composed of minerals that, let me see if I can get this to, whoops, If I go like that, oh man, that may be hard to say. Maybe right there. Okay, right, so this is mineral crystals in there. You can see them sort of, some of the flash in it there. A lot of like sort of orangey, we call it pink. And there's some darker colored minerals there, some lighter, close to white or gray ones. Okay, so that has very visible minerals. As opposed to this rock, which is here, also made of minerals. The light in this room isn't great. Also made of minerals, but these are basically almost microscopic. They're in there, they're just really small. You can't see those mineral crystals. So that's what I'm talking about. right? So if you have a natural granite countertop in a bathroom or in a kitchen, that is often natural stone from the ground made of minerals. The minerals are usually pretty large. You can see them. It gives some of its appeal and beauty, and that's why those are popular and quite expensive, actually. And there are many different types of minerals on Earth. There are over 3,000 different minerals. Okay, some of them are super rare, and we only find them in a few places on Earth, or they would be, 30 miles below the surface. But we have other minerals. There's a chunk of minerals that are more common. We see them in most rocks, and you'll see them actually. The common rock-forming minerals, as they call them, on the this is your reference table. On the back page of your reference table, there are 21 common rock-forming minerals. So we will get to this as well. So now, what makes something a mineral? What is a mineral, or what kind of characteristics does it have to have for that item to be considered a mineral? So, first off, it needs to be solid, okay? And the example I often give there is like a liquid water is not a mineral because it's not solid. But ice is solid, so ice is a mineral. It has to be naturally occurring. It can't be man-made. So it has to be naturally occurring, occur on Earth, and not made by man. And it has to have a specific, so solid needs to be crystalline. So it actually will have crystals forming that make it up. And then we saw this here in this rock here. We can see, and I get, right, you see the mineral crystals on here. That's what that is. This actually looks okay right there, right? Mineral crystals. So it has to be crystalline, it has to be naturally occurring, it has to have a specific composition and atomic structure. So what are the atoms that make it up? So the salt, the table salt, or the mineral halite that I just referred to before, the chemical composition is NaCl, sodium and chlorine bonded together in a specific structure, which we'll talk about. It has to happen. It has to be inorganic. Now, the word organic, I think in modern society, the use of organic, or the word organic in the grocery store, is actually a little different than the scientific term. Oftentimes I ask what organic means, and kids say in the grocery store, it means no chemicals, or it means natural. And that's not really the meaning. The meaning organic means organic means from a living thing. Inorganic means not be from a living thing. So that's important. So for instance, coal is actually from a living thing, is from dead plants that we decompressed, although coal is a rock, but so not from a living thing, and that's what minerals are. So, okay, let's keep going to the bottom part of that page. So the most abundant elements, so now we're talking about atoms here, most abundant elements are types of atoms on Earth are silicon and oxygen. People often get surprised at that, and they go, oxygen, you mean the air we breathe? Well, we breathe oxygen gas, and that's O2. There's two oxygen molecules bonded together. Here we're talking about single oxygen, and that actually makes up most of the crust of Earth is silicon or oxygen. Back to this rock right here, also a little before, this is mostly silicon or oxygen, believe it or not. So, and these are called silicates. There's a whole category of minerals that are called silicates, and they are the most abundant mineral group on Earth. And this is sort of the close-up of what they look like. So they're commonly bonded together in a form called the silicon-oxygen tetrahedron. So copy that down as well. Right, so a tetrahedron is this shape here, and the silicon in the middle, and the four larger oxygens around it in this shape. And then when you have, now that's just one of them. In a real mineral that makes up rocks, you're gonna have many, many of them bonded together. They're billions and billions of these things. So these are really, really small. Even a traditional microscope can't view them. So what we have here is this. So that's silicon. These are four oxygens. So the chemical formula of this is SiO4, one silicon to every four oxygens. And then what you have here is, this is the atomic structure of the mineral quartz, one of the most common minerals that there is on Earth is quartz, and it's many of these bonded together. So please copy this down. Silicon, oxygen, tetrahedron bonded together. Copy that down now, please. or you can pause the video. Okay. So this is something on the front page of your reference table. The front page on the bottom, there is this chart. And basically, for this purpose, we're going to put the crust of Earth. This is a hydrosphere. Hydro means water, and the troposphere is the atmosphere. But we're talking about this really. And it has the different percentage of the elements here. And by mass is meaning by weight, and by volume is how much space it takes up. So as far as space goes, we saw how big the oxygen atoms are. 94% of Earth's crust is actually oxygen, which is a really high percentage if you think about it. So this is on the front page of the reference table. Know it's on there. We have to use it to answer questions often. So let's keep going. So for instance, this is a mineral called kaolinite, and this is what the atomic structure is. We'll talk about that in just a second. How all of the elements are bonded to each other and what the pattern is. We see another one here. These are more silicates here. These are the silicon oxygen tetrahedrons in these chains. A little hard to visualize how they really work, but these diagrams really help you get a sense of how this works. Okay, so a mineral's properties. Some properties of a mineral would be its color, how hard it is, like resist scratching, how the pattern or no pattern that it might break in, and some other characteristics that we will talk about, whether it shines like metal or doesn't shine like metal. Those are some of the properties. So it depends on really two main things: what it's made of, which would be its chemical composition. In our case, we've been talking about silicon and oxygen, and then and that tends to make sense to people. But more importantly, and I want to stress this, how the elements are put together or arranged or bonded to each other. It's often called the internal arrangement of atoms, or also called the atomic structure. So please pause this and copy that down. And then the second bullet point says minerals made of the same elements can be very different if their atoms are bonded in different patterns. Please pause and copy that. So what happens here is you can have the same exact, like I'm going to say, same chemical, same ingredients, and the actual minerals can be very different. So here's some examples for this. This is a key aspect to all of this. So here we go. Write this down, please. Our example is going to be a box of Legos. May not mean much to you now, but you write that down, and then when you go back and you're studying your notes, it will jar this next thing I'm going to show you. Now, this is not in the packet that you have, but so for instance, let's say we get two of these. They're boxes of Legos. They're brand new in the package, sealed up. We get two of them. We give one to Earl and one to Janella. And we say, all right, Earl and Janella, I want each of you to go to separate rooms and just build something with them. But you got to use them all. And they go, okay, got it. And they come back, and this is what they show us. Earl builds this, and Janella builds that. First off, I got to say, Earl and Janella, good job. Look at this thing. This is pretty amazing. But they basically started with the same exact Lego bricks and the same number of them, but they build very different things, right? So they would have the same chemical composition in this case if it's a mineral, but how they're put together leads them to be very different, and that's the idea of different atomic structures. So, and the key example of this, and the one that I love and people tend to really love, is this. I don't know, this may not look like much to you. This is a mineral sample. It's probably about this big. And this is the mineral graphite. It's the mineral graphite. I hope that you can recognize what the name of that mineral. But many kids can't, and many people can't. But we all are very familiar with it because graphite is seen by most of us every day in school. And it is the point of a pencil. I know that we call it lead. I know they call it lead, but there's actually no lead in there. The element lead is not in it at all. It is actually graphite, which is made of carbon. And it has unique properties. It's very soft. So it's so soft that it is a mineral you rub on paper, and it rubs off onto the paper, which is unique. And The next mineral I want to talk about in the world of atomic structure is this. This is a diamond. This is an uncut diamond. How they find them in the ground, in diamond mines, it would look like this. Now, I think a lot of people may look at this and say, that's not a very attractive diamond. Well, you're right. That is the raw diamond before it gets processed and cut by skilled, very skilled diamond cutters. So what we like to see is when it ends up like this. Okay, this is a typical cut for a diamond and is cut very specific angle and in a very specific pattern to make it the light shine into it and then bounce out of it. It looks very brilliant, and people really like diamonds, and that's one of the reasons they are quite expensive. Now, the interesting thing here, oh, and so some people were like, those kind of diamonds. These are the kind of diamonds that I happen to like the most, and they're on this blade right here. It's like a saw blade, and because of that, diamonds are really, really hard. There's really high hardness, and we use diamond blades to cut. You can cut cement with it, you can cut stone and rock with it. Probably doesn't seem as exciting to most people as this, but I don't walk around with diamond jewelry on my, that's not my thing. I'm more of a get a diamond saw and cut concrete, and I guess this is not sounding good. I'm not, okay. But anyway, enough about that. So what we have here is a diamond and graphite, very different minerals. Graphite has a really low hardness, rubs off on paper. Diamond is the hardest material known to man. And they are both made of the mineral carbon. So they have the same exact ingredients, basically, just carbon. And the difference here is how those carbons are bonded together. A diamond is bonded in this sort of shape right here, which makes it, they're really all really strong bonds, so they're very hard to break. And that's why it gives us such a high hardness. Graphite is in these layers, and then the bonds between the layers are kind of weak, and that's why it rubs off. So graphite crystal structure here, or atomic structure, would be this. We'll talk about graphene, but it looks like this, just another image of it. And what you want to do is then copy this down, please. Pause this and copy this down. Diamond and graphite have the same composition, which is carbon, and their properties are different because they have different atomic structures. So pause this and copy that, please. Okay, moving on. So what we have here, this is the structure of graphite. Again, every single atom here, which are the little circles, is carbon here and here, okay? So this is graphite, and the red bonds between them are pretty strong, but these ones that go like this between them, those are pretty weak, and so you break them really easily. Rubbing just on paper, you break those bonds with just a little bit of force, hence we use it as pencils. When diamond here, it has this sort of shape, and every bond there is really strong, so you rub it on something else. You rub it on metal, it's gonna scratch the metal. Metal won't scratch it, and that's because it is a really, really high hardness that we say there. So let's pause this and copy this down, please. That will really help you. Okay, how do I get this off there? Oh, there we go, okay, great. And then just as an example, we're talking about atomic structure here. This is halite's atomic structure. So halite, again, going back, that is table salt, the salt that you put on your food. It looks like this, and there's Na and Cl, so sodium and chlorine, and sodium and chlorine bond together in this pattern. So that's halite's atomic structure. Great. I will pick up in the next video shortly.